Welcome to Differential Equations and Power Series. So the idea here is many real life situations can be modeled using what is called a differential equation. So many real life situations can be modeled with differential equations. Which are equations that relate sort of the derivatives of a function with the function. So that relate the derivatives of y to y and x or t. Often we use t for time. So as well as some initial condition on y. And it turns out that series can be used to solve these. So it turns out we can use series to solve. So for example, let's say that it is known that the population on the planet Calcula grows at a rate of 0.004 individuals per person on the planet per year. If there are currently 400,000 individuals living on the planet, find a function that gives the projected population t years from now. So what we can do is if we set t equal to the number of years from now, and we set p of t equal to the population at time t. Then we have the rate at which the population is increasing. So the rate at which the population is increasing is dp dt, or p prime of t. So if we're told that this rate is equal to 0.004 individuals per person per year. So a population increases. Okay, so again, we have the population is increasing. At a rate of 0.004 people per individual per year. So dPdt is just people per year. So we need to get rid of that individual. So dPdt, or P prime, is people per year. And so we can get this by doing that 0.004 people per individual. Per year, and multiplying by the number of individuals, which at any given time, the population is the number of individuals. So we multiply by P individuals. And so what we get is that dPdt is equal to 0.004 times P, or in other words, P prime is equal to 0.004 times P. So this sentence that we had, that was the population grows at a rate of 0.004 individuals per person on the planet per year. That directly translates into this differential equation here. We also know that the initial population, or when t equals 0, so the current time, population is 400,000. So that essentially tells us that P of 0 is 400,000. So this is translating that next sentence. So there are currently 400,000 individuals living on the planet. The population is 400,000. So that's what this next piece is. So these two pieces of information together form what is called an IVP, or an initial value problem in differential equations. So our model is P prime is equal to 0.004 P, with P of 0 equaling 400,000. So now the question becomes, what does this have to do with series? So what we will do is we will go ahead and assume that P is a power series. So let's assume that P of t is a sum from n equals 0 to infinity of a sub n times t to the n. Right? So let's first go ahead and plug in P of 0 equals 400,000. So we have then that 400,000 is equal to the sum from n equals 0 to infinity of a sub n times 0 to the n. So again, that very first term, the 0th term, we just have a sub 0, and then we have our higher powers, which will all go to 0. So this is actually just a sub 0, right? So this would be a sub 0 plus a sub 1 times 0 plus a sub 2 times 0 squared plus etc. So everything beyond a sub 0 is just going to 0. And so we get that a sub 0 is actually just 400,000. Right? Now let's go ahead and look at the derivative. So now let's look at P prime. So we know that P prime of T should be equal to the sum from n equals 1 to infinity of a sub n times a to the n minus 1. So we have P prime of 0. Oh, again, let's plug in 0. So if we plug in T equals 0, then we have the P prime of 0 as the sum from n equals 1 to infinity of a sub n times, sorry, that should be a t to the n minus 1, not a. So we would have a sum from n equals 1 to infinity of a sub n times 0 to the n minus 1. So this is a sub 1 times 1 times 0 to the 0th power. We're going to view that as 1. So we have a sub 1 plus. Then we have, actually, let me write the a sub 1 times 1. So we have a sub 1 times 1 plus a sub 2 times 0 to the first power plus a sub 3 times 0 to the second power plus, etc. So once again, everything after that a sub 1 is just equal to 0. So we get that our a sub 1 is equal to P prime of 0 over 1. I know it's weird to write over 1. I'm doing this so we can see the pattern. But we also have that P prime of T is simply equal to 0.004 times P of T. That was our differential equation. So we have the P prime of 0 should be equal to 0.004 times P of 0, or 0.004 times 400,000. So what we get then is that our a sub 1 is P prime of 0, or 0.004 times 400,000 over 1. So now we'll go ahead and look at the second derivative. And we should start to see a pattern developing. So now let's look at the second derivative. So if P prime of T is equal to the sum from n equals 1 to infinity of a sub n times t to the n minus 1, it turns out that the second derivative is the sum from n equals 2 to infinity. Again, that first term is a constant term. When we differentiate, it disappears. It goes to 0. So we keep eliminating the first term. Our a sub n times n is a constant. Derivative of t to the n minus 1 is n minus 1 times t to the n minus 2. So the second derivative, we have the sum from n equals 2 to infinity of a sub n times n minus 1 times t to the n minus 2. Once again, let's go ahead and plug in t equals 0. We get that the second derivative evaluated at 0 is equal to the sum from n equals 2 to infinity of a sub n times n minus 1 times 0 raised to the n minus 2. If we think of this again as our infinite polynomial, we have a sub 2 times 1 for our constant term. Then we have plus a sub 3 times 2 times 0 to the first power, plus a sub 4 times 3 times 0 to the second power, etc. Everything beyond that first term will wind up being 0. And so we wind up getting then that a sub 2 is simply the second derivative evaluated at 0 divided by 2 times 1, or 2 factorial. Again, we also have that p prime is equal to 0.04 times p. So if we differentiate, then the second derivative should be equal to 0.04 times p prime, right? If we do just differentiate with respect to t. And p prime is equal to 0.04 times p. So we have 0.04 times 0.00, sorry, I'm missing a 0 here. We should have 0.04 times p, and then 0.04 times p prime. And we should have our 0.04 times 0.004 times p. There, I just substituted our equation for p prime in. So we have the second derivative of p is 0.004 squared times p. Therefore, we have the second derivative evaluated at 0 should be equal to 0.004. I should stick this in, let me keep my colors consistent. All right, so we have our second derivative evaluated at 0 as just 0.004 squared times p of 0, or 0.004 squared times 400,000. So putting this together with the fact that a2 was the second derivative evaluated at 0 divided by 2 factorial, we get that a2 is equal to 0.004 squared times 400,000 all over 2 factorial. If we kept this up, so if we continued in this manner, we would get that our a sub n is equal to the nth derivative of p evaluated at 0 over n factorial. And we would also have the nth derivative of p would just be 0.004 times the n minus first derivative of p. And therefore, it's simply equal to 0.004 raised to the nth power times p. So that would give us that the nth derivative evaluated at 0 would just be 0.004 to the n times p of 0. Or in other words, 0.004 raised to the n times 400,000. And so we would wind up getting that our a sub n is 0.004 raised to the nth power times 400,000, all divided by n factorial. So we get our function for modeling the population. So the population at time t years from now is, we would do p of t is equal to, we have the sum from n equals 0 to infinity. We have our formula for a sub n. So we have 0.004 raised to the nth power times 400,000, all over n factorial, times t to the n. And of course, that 400,000 is a constant scalar multiple in every single term. We can pull that out front. We have 400,000 times the sum from n equals 0 to infinity of 0.004 raised to the nth power over n factorial times, and then that whole fraction times t to the n. So this is a way we could go about solving this differential equation with an initial condition by using power series. So in the next video, we will move on to the next section, which will kind of play around with this formula for a sub n that we developed here, and use this for approximating functions.